Welcome back to Thermodynamics. We are in class 8. We're going to talk about work of a simple compressible system. All right, so this is section 3.4 from our textbook. And notably, I want to look at the title of this section, work done by the moving boundary of a simple compressible system. That's sometimes we'll call this boundary work. I don't, but the book does. So anyway, let's first take a look at something. Probably the most important thing, takeaway, when it comes to work is the diagram, the pressure versus volume diagram. All right. So when you hear about thermodynamic work, you might want to think to jump right to that diagram. And so we need some explanation of why that's an important diagram. And first we'll start with the definition of work that we've already encountered before. Right? So work is force through a distance. We've said that in the last class. I was very specific about it. When I teach this in dynamics, when I teach work in dynamics, we usually say that we have the force dotted against the position vector. And that dot product means that the two vectors need to be in line with each other. So that word work through means that the force has to be, or the motion has to be in line with the force, I guess vice versa, either way you want to look at it. So there you go. This is our definition of work. But if you think about it, when we're dealing with pressures, because we're dealing with thermodynamic cycles, force is going to be equal to pressure times area, right? So the pressure times the area is going to equal the force. And then, well, if you have area times displacement, that area times the displacement, that's going to be volume, right? So like if we had a piston right here and we knew the area, because through here from the diameter, the distance that it would move through would be the volume that it would sweep. Like, so if it started here and it moved over, it would have like a cylinder worth of volume. That was area times its displacement. So it's not a big jump to go that force times distance is going to get work, but also pressure times change in volume. Now, there's an interesting and important notation that's going on here. Notably that this is a D, or this is a del. This del is an inexact differential, where this is an exact differential. The primary thing that we want to work on, so let's make some, I have these notes so we can write something on them, so I want to model that in I think I just misspelled exact. No, here you go. An exact differential, where this is an exact differential. And so what's important here about this is a path dependent, right? So it's path dependent. Oh, I don't need an E in there. Dependent. I can write neatly. I don't know why I don't during these videos. Maybe I get excited and go too fast. Maybe I should slow the hell down. I mean, what the hell? You're watching it anyway. You could always turn me on to the little speed on YouTube. So let's see. Work is a path function, right? So the work is a path function as opposed to a point function, right? So the point function, we're going to look in, we're going to zoom in locally, and maybe we could take the derivative and see the slope and that type of thing. But when it comes to the path function, it really matters how we get from point or state A1 to state 2. Right, and so here we're showing 3 different paths that you could possibly take, and it matters which path you take. That's not always true with many different things, but it is true with work. It's also true with heat, right? So so we one aspect you can maybe want to really sink in on is work doesn't have at this point, here's the amount of work that's done. It's no, you'll always see it's between 2 points, point 1 and point 2, or let's say state 1 and state 2. It depends on how you get there. right? So a lot of times we'll see we're going to be stacking some weights onto this, and we're going to go like in a gradual manner. And we establish small little equilibrium points along the way, and therefore we could say this is like a quasi-equilibrium process because we've kind of gone slowly through there. And so the acceleration F equals ma didn't matter because you went through little tiny increments of the thing. So that can change how the process is applied in that quasi-equilibrium. So they're showing it right in there. Now, that's probably enough to cover before the next, not the next video, because there's only 5. Let's take a look at some examples, right? So example 3, 4, because these are very short examples, or they could be short examples if I wasn't so long-winded. So this is example 3, 4, and it's fairly straightforward and fast. So I'm gonna try to do the value added by talking about it a little bit more, right? So we consider this slightly different piston and cylinder arrangement where we have a spring involved here. In this example, this piston is loaded. This thing has a mass MP, right? So the piston has a mass, and it's exposed to the outside pressure, and this has a linear spring, right? And so if you can't remember, springs have a relationship where the force is equal to some constant, which is going to be if it wasn't a linear spring, this wouldn't be a constant. And then it's going to have some deformation. And they decided to use the coordinate x, right? So you have spring constant times x equals 4. So this is going to be units of this as pounds per, or force per, that could be newtons. Force per displacement. Here's the displacement, so you get the force out of that. Really important thing you see a lot of times. Also, linear spring and a single point force. So there's this external force right there is being applied there. And the piston traps the gas inside here. And a force balance would look like this. Now, one of the things, this is the quasi-static, because they're saying the acceleration is so small when we have different incremental changes that we could set that equal to 0. So right here, we're just balancing, some of the forces equal 0 in the vertical direction, which for whatever reason they decided to call x. The forces when the spring is in contact are going to be this pressure times the area right here. And this really all should be equal to 0. So I don't know why they didn't write it out as equal to 0. That just always bothers me. But here's the forces up, here's the forces down. That's what they're trying to symbolize right there. I couldn't quite see that. I'll look at the screen instead of trying to see with my glasses, which aren't really great. So right here we have the gravity, we have the outside pressure times the cross-sectional area, and then we have this spring right here that's coming down here, and here's the displacement that's happened onto that. And so right here, we were able to establish, if we wanted to, a pressure, right? So here's a pressure that's built out of all of these parts, right? So, and you showed that it's dividing this force by this area. So we could write that out individually. Here's the atmospheric pressure plus MP, times G. It's the weight divided by the area. So we're going to turn these into a pressure. And we also have this external force of some sort. And then we can also turn this into KS over A squared. And now, I didn't do a good job here. Because we have X, and I put an A right in there. So what I want to try to do is get this as a function of volume. That's my goal in this, is to get P as a function of V, right? To write it in terms right there. So it was already divided by A. Well, I've divided again by A right here so that I could get and multiply by A on the top. So the X times the volume is going to be V, and then X dot is going to be VO, right? And I haven't been very consistent, but I'm going to try to be, and put it in my slash through there, so I'll make sure that's a volume. So we have this volume change. Now, As far as this goes, if this is our goal right here, we could also just lump in a bunch of things that are happening right here. So we could say that we'll just lump this in as a constant, because if you assume all of these are constant and this is the thing that changes, you could say that we have this condition right there. Now I'm going to ignore the VO right there. Well, I'm going to say that pressure is a function of this right here, and we will go ahead and say work through this here in a second. All right, so to explain, I'll say that C1 is equal to PO plus MPG over A plus F1 over A, and C2, these are just constants, is going to be K, spring constant divided by the area squared, not area 2. All right, so with that, and what you can see also from this equation is it's a straight line. This describes a straight line on a P versus a volume, a PV diagram. And so it's a straight line. So if we want to try to get work between states 1 and 2, and they write it differently than I used to, so I'm going to try to stick with theirs. It's going to be the integral of P dV right here from 1 to 2. What you're really saying is you're taking the integral of 1 to 2, and you're going to take this in here, C2 V dV, right? And I meant to put crosses throughout all these things. If you were to work through here and integrate this, you get C1 V1 plus 1/2 C2 V2. Not C2 V2, is V squared. Once again, I'm forgetting this. And you're going to do that from 1 to 2, right? So that's where that 1 and 2 went up right here. So okay, we're going to go from 1 to 2, and normally we're gumming up that way, right there. We're expanding. So and one thing to note is that work is coming into this system, as shown right in there. Or maybe they're just saying that area. The really important thing that you want to remember is that the area underneath this curve right here in a PV diagram is going to be equal to work. And it will, no pun intended, work out to be, in this case, because you could do, okay, so let me say this. Here's the integral. I'm going to jump from this integral back over to here, but I'm going to show in a second how it's close to being the same. But check this out right here. The results of this work are going to be the actual area that are underneath the PV. So that's just a trapezoid. So you could just as easily go P1 plus P2 divided by 2, right? So that's going to be like the average of that one and that one, that height, and then times this distance right here, this distance right there. So it's going to be V2 minus V1. Right. Now, if I made a big leap from here to here because I didn't want to bother writing all of this down. So let me explain, because I did write it down somewhere, and I have hidden it from myself. There it is. Okay. Let me just go through this because I'm not going to go in class, maybe. I don't know. So I just want to show how this works out, right? So we made a jump from here to here. And I just wanted to demonstrate that it worked out. Well, how did I do it? I decided just to demonstrate, with the algebra would work out, that I started from here and showed that I would get the same thing as this right there. So first off, if we were going to get this guy right here, we would end up with this result right there, right? See, I made the pun already. So that's just the same thing as this right here. I've just plugged in those two numbers right there. Then I went ahead and I collected some stuff. Well, I guess that's enough right there. Okay, so I just showed where I would get. Now I went back to this guy and showed I would get the same thing from here to get as I would get from there, right? So that's where I went to there. I decided that I just didn't want to bother with all of the algebra going from the other direction. So here's what I had written on the previous page. notably that P1 and P2 are equal to these things right there. I separated these out as P1 times there, P1 times this, just like you learned in algebra. Separate those things up. And then I substituted. I substituted P1 and P2 into here. And notably, the C2, V1, V2, that one canceled out. But I'm going to have two of these, two C1 V2s and two C1, and they're negative, both of them. It's right here. So you note that 1/2 is going to be distributed in there. So I'm going to have two of these, but the 1/2 is going to get rid of them. I'm going to have two of these, and 1/2 is going to get rid of here. So the 1/2 comes onto there, and the 1/2 comes onto here. And we can see that, and boom, all right? So what we're left with is what we've just shown is that this is the same thing as this right here, all right? I don't know if it was worth coming over that, but I just wanted to point out, I've always disliked when people just jump from one thing to another. So we could get this same result from doing the integration. So this is the area method, right? So because this is a trapezoid area, but this up here is the integral, where you are now replacing the pressure as a function of volume with this convenient equation and demonstrating that you would get the same answer either way. That was a long way around, but I don't know, maybe worthwhile. I think there's another example that I might not want to bother with I don't want to bother with a new video just for this. So I'm going to go ahead and cover this because this is in the textbook, but it's not really essential. I found that I think that it's sort of, I guess maybe there's a couple things that might be interesting. So that they set up another scenario where they have this little pin right here, and they have a pressure here and external pressure there. And I think, yeah, this thing does have some weight to it, right? So the piston and the gravity and over this area, but they're going to let go of this pin and see what happens. Now, it appears to me that what they're showing in the graph is that when they let go of this thing, that the weight of the piston is so much that it starts to go downwards. No. This is the pressure, right? So P1, yeah, okay, so yeah, this must be going upwards. So it starts to push this thing upwards, but then, so the pressure is decreasing, so the motion must be going upwards, right? But then it hits like a peak, and then the weight of this starts to take over, and it's going to start increasing the pressure, and it's going to have, and eventually it's going to come down to a balance. And we're going to assume that we're not losing anything, which isn't really true. So what you might find in this is all the areas underneath there are going to would balance out, right? So that was probably the lesson or the takeaway, I think, that when I was reading this, that I was like, oh, this is an interesting thing that you might want to take a look at. Now that's time, I'm sure, but it's not. So it's not volume, but the areas do represent some. We could even think of them as impulses. Don't worry about that. But force times time is impulse. So you could think along those lines, and you can see that we come to an equilibrium state right there. I think that's about all I really cared about. You could also say that that these were because there were no other forces going on here, right? We had like external forces and internal forces, that they would balance each other out. That the external work would eventually be zero, I think, is what we're saying, because there wasn't any external thing that's happening onto it. Anyway, that was all I wanted to say in that example. You're welcome to read it and look at it a little more closely in the book, but I don't think it's as important as the next examples that we're going to run through.